So, as we're moving into chapter 6, we're going to be talking about applications of the integral, specifically applications of the definite integral. So, I thought it might be a good time to review how we kind of motivated the need for the definite integral back in Calculus 1. And we tended to start off with the scenario where we're trying to estimate the area underneath of a curve. And the way we did that is we used Riemann sums. So we took the region uh, between A and B on the x-axis under some curve f of x, and we broke it up into a series of rectangles in the way that I have sketched out here. So we've got this curve f of x, and I don't have it written down here, but this first point x sub 0, this is essentially A. So this is where our interval begins, and then over here at x sub n, this is B. So that's the end of our interval. And what we've done is we've gone through and we have broken up this entire interval on the x-axis into n subintervals. So we 1, 2, 3, 4, 5, 6, 7, all the way up to n, and we can determine that later. And what we're going to do is we're going to try and calculate the area of each of these rectangles and then add them all up together, and this gives us an approximation of the full area underneath the curve. So how do we generalize the area of one of these rectangles? Well, let's focus on the kth rectangle right here. So this is our kth rectangle. Now the area of a rectangle we know is just the width times the height. So how could we generalize the width and the height of this sort of abstractly defined rectangle? Well, the width is going to be the difference between these two x values, x sub k and x sub k minus 1. So as we start to kind of keep track of things over here, we could say that the area of the kth rectangle, and I'm just going to call this a sub k, and that's going to be equal to the height of the rectangle times the width of the rectangle. So now we have to define these two quantities. So we already talked about the width, so let's kind of deal with that first. So the width, we're going to say that this is going to be equal to whatever that point x sub k is minus the point right before it, x sub k minus 1. And we're going to go ahead and refer to this as the change in x sub k on the kth subinterval. So we'll just call that delta x sub k. Now, how do we find the height? The height is a little bit trickier if we're not thinking about what we have here. So let's go back to our rectangle. So the way that we defined the height of this rectangle right here is where it hit the curve, where the top of the rectangle hit the curve. And we defined that by choosing some point on this subinterval and bringing it up to the curve. So I'm going to call that point right there x equals c sub k. So some little point in there. And this value, this distance from the x-axis up to there, is defined by the y value of the function at this point, which we would just call f of c sub k. So that's going to end up being the height of our rectangle. So now we can go ahead and put that down. So our height is going to be f of c sub k. So with these two quantities, we can now go ahead and specifically define that the area of this kth rectangle is going to be f, whatever our function is, evaluated at c sub k times the change in x over that kth subinterval, delta x sub k. All right, so what we're going to do is we're going to add all of these up together, and we're going to get an approximation. So with the idea in mind that we want to get as best of an approximation as possible, what we may want to do is let the number of rectangles, n, get larger. If we have more rectangles, that's going to minimize these little gaps where we've got overestimate right here or we've got an underestimate right there. So if we were to let n get larger and larger and larger, that's going to give us a better and better approximation. So we're going to make a couple notes here. So if we were to let the width of this rectangle, delta x, and we're going to kind of even that out, and we're going to let that be b minus a divided by n. So we'll just say the number of rectangles, we break up that interval into equal subintervals delta x. So we can consider that. Now we also said that we're going to let n get infinitely large. So n is going to approach infinity. So we ask ourselves, well, what is that going to do to the width of each of these rectangles? Well, if we increase the number of rectangles, their widths are going to get smaller and smaller and smaller and smaller. And if we cram in an infinite number of rectangles, the width of these is going to approach 0. And that led us to a means of expressing the actual or the exact area under this curve. So we then said that the area is going to be, we're going to bring limits in here. So the limit as the number of rectangles approaches infinity, and then we're going to add all of these areas up. So we're going to say the sum of each of these areas from the first rectangle to the nth rectangle. And we've already defined the formula for area. So it's going to be the sum from the first rectangle to the nth rectangle of f of c sub k times delta x sub k. And as we let this, and we actually don't even need that sub k anymore because we've normalized that width up here by saying it's b minus a divided by n. And we know from Calculus 1 that this leads directly to how we define the definite integral. So that's the integral from a to b, our endpoints, of our function f of x dx. So we're going to kind of build on this idea of if we're interested in the value of a whole, let's consider breaking that whole down into manageable pieces and then adding all of those individual pieces up together to get a full value.